have two, or I guess we have one talk and kind of a discussion following that. So we'll start with Zephu Dai and his work with Jinwen Zhu.
Yeah, okay. Thank you for the introduction. I'm going to try to be short because I know there's an important talk after me. So my talk today is the multiple memory controller design. So there are many different types of electronics. These are some of the ones I like to have. They all have very different fancy appearance. However, if you look deep inside, you can find similar pictures of SoC platforms. Most of them using common components like multiple memory controller, which has great impact on the performance of a gadget in your hand. So the first question is, there are already many MPMC designs. Which one do you want? Here's an example portable media player SoC. In the top left, there's a general purpose processor running rich operating system and audio processing. In the middle, custom hardware implements an H.264 video decoding. There's also a DVI controller driving a display. All the processors are connected to a common multiple memory controller, which arbitrates access to the shared DRAM memory. The first challenge of the MPMC design is that the bandwidth requirement is actually quite different. In fact, the difference can be as much as 1,000 times. Another challenge is that the timing requirement is also different. So, for example, the DVI controller may require a fixed rate low traffic. The video decoder, while the video decoder will require a large amount of data in a shorter period of time. And the CPU will say, oh, I want to have my service be satisfied as soon as possible. However, the bottom line is that the DRAM memory has a limited theoretical bandwidth and access latency. Adding to the challenge is that the DRAM performance is very undeterministic. So the major DRAM operation is pre-charge, row activation, and column access. Only the column access command are doing useful job. So here are two diagrams showing the timing of consecutive access to the same row and the consecutive access to different rows. The latency can be up to an order of magnitude difference. So it is important to avoid row conflict or page crossing. Page crossing is also expensive in terms of power consumption, because you will incur a pre-charge and row activation commands pair, which will send tens of thousands of bits into the row buffer, and which will cost a lot more power than the useful column access command. So, so if we can reduce the power crossing rate, we can maximize the effective DRAM bandwidth. Now come back to our first question. Which MPMC do we want? Here are the features we like to have, including the minimum bandwidth guarantee, minimum latency guarantee, and maximize effective DRAM bandwidth. And hopefully we don't have the hardware cost is reasonable. So previous work have trying to address the challenges of MPMC designs. They made different achievements on different aspects of the problems. However, none of them has succeeded in covering all the requirements, and also notice that few of them has actually been aware of the restive bandwidth. So in order to meet all the objectives, we try to leverage three key observations of MPMC designs. The first one is the port locality. We think that requests from the same port are more likely to fall into the same DRAM pages. The second observation is that the bandwidth guarantee can be actually very flexible. For example, each video frame has 124 seconds of timing budget, which translates into 4 million cycles in a 100 MHz clock. The last one is the restive bandwidth, because port may become idle, and so there's restive bandwidth at runtime. We actually propose a separate method to exploit the benefit of these key observations. We choose weighted absorbing for port locality because it provides easy support for bandwidth guarantee and Bursty service for different ports. For the bandwidth flexibility, we employ the credit, borrow, and repay mechanism to achieve minimum latency guarantee by request reordering. And for the Restive bandwidth, we actually devise a dynamic bandwidth calculation scheme to capture the Restive bandwidth at runtime and use it to accelerate important traffic. So weighted route-robin is very familiar to most of us. Assume there are three ports with different weights in terms of bandwidth. Also assume that the WRR takes 10 cycles to schedule each route, to finish each route of scheduling. I would like to illustrate the scheduling process using this figure. So the top row shows the clock cycle. We use a separate row to show the request arriving time for each port. Also, another row is used to show the service time of each port. In the first cycle, there are 3 requests arrive to each port, and the WR scheduler chooses to service port number 2. In the second cycle, another 3 requests arrive and port 2 get the service again. In the third cycle, 2 more requests arrive and still port 2 get the service. Now the port 2 has already exhausted its scheduling credit. The WR will switch to service port number 1, so on and so forth. So the Q0 only gets service in the last 2 cycles. We can see that the WR can support a Bursty service for each port. So by leveraging the port locality, the WR scheduler can actually achieve like 1.5x improvement in the effective DRAM performance when scheduling the same sequence of requests from 3 different ports compared to the route-robin scheduler. But the problem with WR is that it has limitation on latency. For latency-sensitive ports, it has to, on average, it may need to wait for a very long time. For example, although the Q0 has the highest priority, but you need to wait up to 8 cycles before getting scheduled. And this waiting time could be much larger if the WR takes more than 10 cycles to finish each route of scheduling. We solve this problem by the credit, borrow, and repay mechanism. To illustrate the credit, borrow, and repay mechanism, we attach a data queue to Q0, which is basically a FIFO. So now let's restart the scheduling process. In the first cycle, 3 requests arrive, and the scheduler chooses to service port number 2. However, because there's higher priority request in Q0, it actually borrows the scheduling process from Q2 and send its request to a DRAM. In the second cycle, we can see that the data queue is updated with the port ID of Q2. So it reminds the Q0 that you are actually in that. So it later borrows another scheduling opportunity from Q2 and sends another request. In the third cycle, because there's no more request in Q0, Q2 can keep the scheduling opportunity to itself and send a request. The credit, borrow, and repay mechanism doesn't touch the baseline scheduler. So the WR scheduler actually switched to Q number 1 as nothing has changed. Later, when there's no request in Q0, everything will happen exactly the same as before. And in the end, when Q0 gets its scheduling opportunity, if there's no request in its queue, it will check the data queue and it start to repay the scheduling opportunity to Q2. Then Q2 finally has the chance to send the rest of its request to the DRAM. In the end, the data queue becomes empty and the bandwidth guarantee is recovered. So we can see that with a data queue, with a depth of 2, the data queue can provide minimum latency guarantee to Q0. However, there's limitation for the credit, borrow, and repay for the CDR mechanism. This is because it depends on the depth of the data queue to provide minimum latency guarantee. Okay. So the limitation of the CBR is that it relies on the depth of the queue to provide minimum latency guarantee. However, the depth of the queue is limited, and the instantaneous bandwidth requirement of the ports can be orders of magnitude higher than its average bandwidth requirement. What's that? Live stream. So it will be. So this picture shows the bandwidth requirement of a CPU cache over time. It will be very impractical for the CBR to provide minimum bandwidth guarantee for such type of applications. Okay, so fortunately, we can use the Restive bandwidth to help reduce the requirement for the CBR mechanism. The Restive bandwidth is the bandwidth allocated to a user based on use at certain periods of time. By identifying the Restive bandwidth as runtime, we hope to allocate the Restive bandwidth according to the priority, instead of sharing it among all the users. So it turns out that we can allocate the Restive bandwidth to help repay the debt. Assume there are four requests in Q1, and there are 3 requests in Q3. In cycle 7, the WRR scheduler will switch to serve Q0 because there's no more request in Q1. So Q0 can send its last request to the DRAM. Then in cycle 8, Q0 repay the credit to Q2. However, it still have one more entry of that in the debt queue in cycle 9, and Q0 has already exhausted its scheduling credit. If we can reuse the Restive bandwidth of Q1 to repay the debt, so in the end, the Q0 will enjoy an empty debt queue while it will get its actual request being serviced. By doing this, we actually allocate the Restive bandwidth to Q0, and we reduce the requirement for the debt queue, for the depth of the debt queue. The question now is how can we identify the Restive bandwidth? When a queue doesn't use up its scheduling opportunity allocated by the WR scheduler, it doesn't necessarily mean it is Restive bandwidth, because that credit may be used later by requests arrive later. Actually, we believe the WR itself doesn't have enough information to identify the Restive bandwidth. To be able to identify the Restive bandwidth, you first need to define it formally. Suppose each round of WR scheduling takes T round of cycles. We can model the bandwidth allocation process as each part accumulates fractional bandwidth every cycle, and then use them all during the service time. So now for the bandwidth allocated to port X at the time T, if we can make sure that this bandwidth is not used in previous T round of cycle, and will not be used in the future T round of cycle, we are safe about that this bandwidth is Restive bandwidth. So in order to come to draw such conclusion, we devise a new dynamic bandwidth calculation scheme. We use dynamic credit to represent the bandwidth utilization status for each port, and static credit to represent the fractional bandwidth allocated to each port every cycles. Now in the beginning of each cycles, if the sum of the dynamic credit and the static credit is smaller than 0, that means the fractional bandwidth has been used in previous cycle. If the sum is larger than 0 but smaller than a threshold value, it means this bandwidth could be used in future T round of cycles. Otherwise, if the sum is larger than a threshold value, we know that this bandwidth is Restive bandwidth, and we can reuse it to something else. So finally, this is our final algorithm. We call it Bursty Credit Borrow and Repay, BCBR for short. I hope you notice the line number is it means to tell you it is concise and simple. So in order to evaluate our algorithm, we build a simulation framework with the help of Mark Jarman from Altera. This framework includes a cycle accurate simulator for the DRAM memory, which is a DRAM sim by Bruce Jacob. it can simulate not only performance but power consumption too. We drive our multiport memory controller C model with different type of workload choices, including CPU cache workload and multimedia workloads. We set the depth of that queue to 16. We test using a 64-bit DDR2 memory. Finally, we compare our test result with priority queuing, route robin, weighted route robin, and CreditBorrowRepay schedulers. We first went. So this picture shows the CPU, the memory access characteristics of the CPU workload. It features irregular memory access pattern and low bandwidth requirement at 20 megabytes per second. The ALP bench suite of parallel multimedia application is selected as the source for the accelerated workload. So this application includes image processing in the form of face recognition, unpacked to video encoding and decoding, graphic processing in the form of ray tracing, and audio processing in the form of voice recognition. The second column of the table shows the number of line of code, which indicates the complexity of this application. And the last column shows the bandwidth requirement, which is quite high. This picture visualizes the memory trace file for the unpacked to encoder workload. It has much higher bandwidth requirement than the CPU workload, and it features periodically repeated memory access pattern. We first want to examine if our proposed scheduler can achieve bandwidth guarantee. We set the bandwidth guarantees for different port as 2% for port 0, 30% for port 1, and 20% for port 2, 3, and 4. The table here shows that the route robin scheduler and priority queuing scheduler cannot provide bandwidth guarantee, while the CBR, WR, and BCBR provide fine-grained bandwidth guarantee to each port. We then compare the effective DRAM bandwidth achieved by different scheduler. We can see that the weighted route robin in our scheduler achieve much higher effective bandwidth in the image processing, graphic processing, audio processing test cases. At a bandwidth of about 2 gigabytes per second, this is nearly 50% of the theoretical limit. And our proposed scheduler actually achieved on average 1.5x more higher effective DRAM bandwidth than the route robin scheduler. We derived the energy efficiency from the test results. The BCBR scheduler actually has 30% less page crossing, and therefore 1.47x more energy efficient. This indicates how successful we are in leveraging the port locality. We later want to examine the minimum latency guaranteed. On average, in terms of CPU cache response latency, the proposed scheduler is on average 2 times faster than the route robin scheduler, and 11 times faster than the weighted route robin scheduler. We think the priority queuing set a lower bound on the latency you can achieve for high priority ports, and we can see that for all cases, our scheduler achieves the same latency as the priority queuing. So this concludes that our scheduler can provide minimum latency guarantee. So what if there's no restive bandwidth? We show that with a depth of 16, the DAC queue cannot provide minimum latency guarantee alone. And there's average 5x slowdown on the CPU response latency, CPU cache performance. We also want to compare the area cost with Linux 8-port multiport memory controller, which uses route robin scheduler by default. The results are collected from Vertex 6 FPGA. Because Linux MPMC include both front-end and back-end memory controller, we paired our design with a speedy back-end memory controller, which is also designed for Vertex 5 FPGA. We can see that our design has less hardware cost but comparable clock frequency. So conclude, our design meets all objectives. It is simple, it has low hardware costs, and most importantly, it works. Thank you very much.
Any questions?
Have you had a chance to try this in hardware, like connecting it to a processor or other cores?
Yeah, actually, we have implemented this
Oh, cool.
in FPGA, and it works, and show nice picture on the screen.
Okay, good. Thank you, Aaron. Another one?
Could you go to slide 34? I just didn't get enough of a look at that. I think it's 34. So here you're showing that you met the requirements with the bottom 3. Is that right? The bottom 3 routines?
Yes. So this is a weighted resolving results for the bandwidth allocations, right? So for port 0, it requires 2% of the bandwidth, but it actually only uses 0.9%. For port 1, it requires 30%, but actually there are residual bandwidth, and it will be allocated to the port 1. Actually, the residual bandwidth is shared among all the rest of ports for the WRR scheduler case. Also for the BCBR scheduler, the residual bandwidth will first be assigned to port 0. If port 0 doesn't use up all the residual bandwidth, it will be shared among all the other ports.
Because port 0 is got the higher priority here?
Yeah, because port 0 is implemented with the CBR mechanism, the dot queue, right? But you can easily extend the dot queue to all the ports. So the residual bandwidth will be allocated according to the priority. Like this one, so all the residual bandwidth will be first go to the port 1. So it will have much higher bandwidth than it requires. And then the rest of it only get the minimum bandwidth guarantee.
And so what are those numbers showing? That in a simulation, this was what was actually used or allocated?
Actually used.
Actually used by
Yes.
running?
From the DRAM sim results.
For that table, if I use a priority queue, that ports 3 and 4 are not used?
Yeah, if you use priority queue, right? Because there's a request from high priority ports all the time, so these 2 ports get stopped. You get no chance to send its request. And for the resolving case, if everyone is failed.
Okay, good. Just thank the speaker.